that to x1. Okay. Second component, pretty analogous. Map f2 f, apply that to x2. Okay? So the functorial action of the pair, right? When you want to define map at a pair, well, it was on the board before, but it's not anymore. What you do is you just recursively apply map to the two components of the pair. Because the left-hand functor tells you how to coerce the left-hand side of the tuple. The right-hand functor tells you how to coerce the right-hand side of the tuple. You put those together to coerce the whole tuple. Good? OK. What about the constant function, constant functor? Well, in this case, because the constant functor applied to anything is a, we just have to go from an a to an a, so we just return x. So the action of the constant functor is constant. OK, so now we've written map is, sorry, the identity. Yeah, I keep saying that wrong. Yeah, yeah. Good, 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 good. Question? So we got Agda to accept that. All right. So next, why don't we do the example and then come back and do the properties? OK. So let's do an example just to illustrate how one would use this library. So if we scroll down to the example, here I just created some 2 hunks of data. So what this says is that a database, databasey sort of thing, is a list of tuples where a tuple has a natural number and a string and a nat cross nat cross nat. Okay? And I've given 2 hunks of data, European and American. And can anyone spot the difference between the two? The dates are swapped, right? OK, so let's use our functor library to turn the European database into the American database and or vice versa. OK? So how are we going to do that? We want to write a program using this library that takes a European-style database and flips the dates around to come up with an American-style database. OK. So any suggestions? Write a functor. OK, write a functor. What functor do you want to write? So the functor describes the place to apply the transformation, right? So the functor is going to say, where in this data structure do we want to apply a function? So let's call the functor there, maybe capital there, just to match the support code. OK. And there is going to be defined to be the functor that says, we want to apply some function there in the data structure. So where in this data structure do we want to apply a function? We want to apply it, yeah, the first column of the third component of the tuple. OK? So let's describe where that first column of the third component of the tuple is. OK? So what's the, basically now we want to write a type that describes the shape of the data around that column. Okay? So what's the shape of the data around that column? What's the outer thing? So if we, can we get, yeah, great. OK. So what's the outer form of the type around that data? What's the first connective? List. Good. What's the next thing? Well, the first component of the tuple is a nat. When we apply our transformation, do we want to change that nat? No. So what functor do we want here? Knat. Good. OK. And now we want to make a product functor times. Did you do a backslash times there? Oh, the product functor is called little x. is this a backslash times slash is the thing you wrote as the functor a little x?
No, it's a ASCII x.
Okay, great. Sorry. In the support code, it's a backslash times, but yeah. Yeah. No, so we're good so far. Right, so what that says is it's a list of things. The first component of the things is a nat. We're going to leave that fixed. The next component of the things is a string, and we're going to leave that fixed. So how do we leave a string fixed? Okay, string. The next component of the list, the next field, is where we want to hit the data with the transformation. Okay, so how do we say that? X. The next component is where we want to, is something that we want to leave unchanged because we want to leave the year the same. Okay, so how do we say that? Knat. Okay, so there is a functor. And let's check just by writing test colon there of nat cross nat. So here the cross is a backslash times. And then define test to be American. There, and then c dot nat times nat. OK, so what we just checked was the value American is of the correct type to apply for this functor applied to nat times nat. Right? So if we plug in nat times nat into the function interpretation of the functor, we get the type of the American database and also the European database because they have the same type. OK, good? All right, so yeah. Yeah. So basically, there is giving you directions. And it says, inside this list, leaving the key the same, the name the same, look at the month day and leave the year the same. Okay? So the x is the spot you're actually applying it to, and the k is all the stuff around that. Yeah?
But isn't the date nested inside?
Oh, so the tuples are right associative. So let's just put in the parens. Yeah. Yeah, so the tuples are right associative. If you want, you can put parens, not there, but there. And then before the x. And you'll note that I picked the example so that the date itself was a tuple so that we could do this, right? So like there's one, if you go up to the type of DB, there's one left associated tuple there just to make this example work, right? Because we want to be able to find the month day or the day month. Good? OK, any other questions? OK, so now that we've got our functor, what do we do with it? So we've written down a functor. How do we convert? Let's write a function called convert that takes a database and returns a database. OK. And how do we define convert? Map, right? We want to say apply some function somewhere. OK. Where do we want to apply it? We want to apply it there. OK. So we're going to use this functor there and map there something on D. OK. And if we load that, then we see that what we need is a function from, well, you can't read the first component of the sigma, unfortunately, when it prints it out. But it's really nat cross nat to nat cross nat, right? Because we want to transform a day month into a month day. So let's write a function called swapf that has type nat cross nat, arrow nat cross nat. OK. And how do we swap xy? Return yx. Okay. Yeah, we could have put an anonymous function, but I'm going to name it because I'm going to want its name later. for reasons that are mysterious at this point. Okay, good?
Why don't we swap passing through swap?
For reasons that are mysterious at this point. Okay. It's the swap function. We might be defining a swap something else in a little bit. Well, yeah, that too. Okay. Okay, so now we can fill that with swap. And so if you read this code, it's really nice, right? There is the thing that describes where we would like to apply the transformation, right? And swap is the transformation we would like to apply. And because our data structure can be described by an instance of a functor, we can all at once reach inside that list of tuples of ... hit one particular bit of it with a function, okay, and apply it. So let's test this. We can write a test. So let's call it test : and then we can say, let's test that convert applied to euro equals American. Okay, let's call it test prime. Okay, and then we can fill in test prime with reflexivity, the constructor for equality that says, hey, please check that these two are equal. And the file loads, which is not super exciting, but it means that the test worked. Okay. And similarly, let's copy that and do one that says convert of American equals euro. And that test worked too. Okay. So what we've got is a function convert such that we can convert back and forth between these two things. So we've used generic programming via an inductive universe to define this map library. And now we can go back and prove some things about it. Okay? So let's prove the properties of map that we would expect to hold, right? So remember I said that map is supposed to preserve identity functions and compositions. Okay? So let's do a proof. Let's call it, yeah, okay. Yeah, great. Just comment it out. We don't need it. Okay, great. Okay, so let's do a proof called map hyphen, I think for time, let's just do one of these, and let's do map fusion. Yeah. Okay, so we can call it map fusion, right? You did one instance of this back in one of the labs at some point, yes? So what we're proving here is a program optimization that says that if I do two passes over a data structure where I just feed one to the other, I might as well fuse that into one pass. So that's going to say that for any functor f, and any functions, any types, any sets A, B, and C, if you give me f, which goes from, or did we do it at G? Yeah, okay. If you give me G, which goes from B to C, and f, which goes from A to B, then it's the case that map of f on G compose f, that's actually just a lowercase o, apply, so actually let's do it in an applied form. So up there, let's parameterize by an x colon a. Okay, so for every x colon a, and I think that one should be explicit. Sorry, let me just look at it. Yeah, so explicit x, yeah, of in A, right. Okay, so what we're saying, let's just get the thing on the bottom on the line and then I'll read it. So if I map G compose F and then apply it to the data X, that is the same as mapping G and then applying that to mapping F and then applying that to X. Okay? Yes, just a lowercase o.
Is G and F case?
Yes, thank you. Yeah.
G and F case specifically, or?
No, in the sense that I wrote the code and it's on the sheet of paper and it's fine with them implicit. Okay. So the property we're proving is that map distributes over compositions. So how do we prove that? Well, we're actually just going to be able to, so let's put in a capital F as the first argument and then lowercase x. And this is just kind of a bang it out kind of proof. So what are we going to k-split on? F, right? Okay, now we have some cases. I don't know, let's try the identity x case first. Okay, what we have to prove is that g of f of x equals g of f of x. How can we prove that? REFL. Okay, now we have to prove over here that, yeah, let's do that one. X equals x. How are we going to prove that? REFL. Okay, now for lists, I don't think this property is in the library, so let's just split x, right? So let's look at the goal here. And if this is going a little fast, it's in the file we handed out, so you don't need to type it in. Okay. What we need to do is we need to prove the corresponding property for list.map of blah, 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 blah with f and list.map of blah, 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 blah. Okay. So if we had this property of list.map in the library, we could use it. But instead, we can just prove it here in line. Okay. So let's just split the list x. Okay. And then in the case for empty, the goal reduces to empty, right? You guys did this proof in lab, right? When you proved map fusion for vectors once upon a time? Yeah. Okay. And then in this case, we need to know that some stuff equals some other stuff const onto some stuff. Okay. So let's use a function called app2. So the idea with app2 is that app2 says, if you give me a function f from a to b to c, and you give me a1, which is equal to a2 in a, and b1, which is equal to b2 in b, then I will conclude that f of a1, b1 equals f of a2, b2 in c. So you want to think of this as a congruence principle for equality, or something like contextual equivalence kind of principles like Amal was talking about, right? You think of f as some sort of context. It's a function. And if you take equals here and equals here, then you get equals down here. Okay, so that's built into type theory. So we can apply app2 to the cons function. So app2 of cons, question mark, question mark. And then if I'm right, unification will work, and we'll get two nicer goals. OK, good. OK, so first what we need to prove is that map f blah, 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 blah equals map f blah, 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 right? So map f of g compose f is the same as map f g compose map f f at x. Why is that true? Inductive hypothesis on, so we'll call map fusion on f, the functor f, which is the argument to list, on x. Okay? And then if you look at the next one, we need to know that list.map stuff, list.map f compose g, list.map of g compose f is the same as list.map of map fg, and then list.map map ff, okay? Which if you, can we do a non-normalized? Oh, no, we can't. Okay. If you do a non-normalized one, it might be the case that Agda will actually tell us the thing I'm about to observe, which is this is really just the recursive call, right? This is really just the same thing for list expanded out one level, okay? So what we can do is we can do an inductive call to map fusion on list of f with x's. Okay. And if you did the proof in lab, whatever, for doing map fusion for vectors, hopefully this is the proof that you came up with, right? Which is in that case, there was no recursive call on the head, but you just kept the head the same and then recursively munched the tail. OK? OK. And we can leave off the times case. I don't think that's really any more illustrative than what we have here. So let's state the identity principle just so we have it. So map ID will have type given any f, which is a functor, given any a, which is a set, and x in f of a. And this code is all in the files we handed out if you're having trouble typing along. I know we're going a little fast. OK, so what we want to say is that if I map the identity function, so map of, let's call it lambda yy, or map of f lambda yy, and then apply that to x, that's the same as x. Great. If I start with the identity and I lift it along f, then it's still the identity. OK? And we won't do the proof of that, but it's essentially isomorphic to the proof for map fusion. And it's in the notes, and it's in the code that we handed out. OK? So what we've got here now is a functor library where we've got a definition of what it means to interpret each functor as a type constructor. We've got an operation called map for each type constructor. And we've got proofs of the composition and unit laws. OK? So let's go down below and use this to certify something about the convert function that we wrote before. OK? So what can we prove about convert? Here's one property for convert. Convert is self-inverse, right? If we convert American to European and then convert European back to American, we get back where we started. So let's define the notion of being what's called a bijection. OK? So first, let's define a type is bijection. And is bijection is going to take two types, A and B, implicitly. And if you want to stop typing along here, this is going to go a little bit faster than you might be able to type, but it's all in the support code. So two types, A and B, and then a function f from A to B, and return a set. And the idea is that is bijection is going to represent a proof that this function f is a bijection between the sets A and B. OK? So what does it mean to be a bijection between A and B? There's an inverse. OK? So we're going to define bijection to mean is bijection with a sigma type. So we're going to say there exists a G from B to A such that it's inverse to f. What does it mean to be inverse to f? It means for any element of x, if I take x, I run it through f, and then I come back through g, then I get back where I started. OK, so first of all, if I start here, run over here, and then come back, I get back to where I started. OK? Second of all, if I start in B over here, take an element y in B, run it over here, and then come back here, I get back to where I started. OK, good? So bijection is just a triple of an inverse function f along with proofs that the composites are the identity. So basic discrete math class, you just type in the definition. Okay? So now let's define a bijection between types A and B. A bijection between A and B is going to be what? When is there a bijection between A and B? Yeah, right. So if there exists a function f, so sigma of f from A to B, such that f is a bijection, right? And if you expand it out, I'm just writing this in a funny form, right? It's really saying there's an f, there's a g, and when you round trip in either direction, it's the identity. So we've expressed the notion of bijection like this. And so now what I'd like to do is to prove that map takes bijections to bijections. Okay? So if we, let's call it map is bijection, and what that will say is that whenever you have a functor f, and you have two types A and B, if you're given a bijection f, then when I map f on, so I take my functor, I apply it to first of f, then that is a bijection. Okay? So we're proving that if you start off with a bijection, like the swap function that we defined before, right? X to y comes back to y to x. Then what you get at the end of the day, after you apply that inside that database, is still a bijection, right? So we start off with a function swap, which is a bijection. We wrote that map there of swap to apply it inside the database. Now we're going to prove that the end result is a bijection. So how do we do that? Let's first case analyze little f. Okay, so f here is really a bijection. So you can actually just write out four components, f, g, alpha, beta. Right, so space before the comma. Okay. Okay. So let's prove that map is a bijection. Why is map a bijection? Well, what do we need to do to prove that map is a bijection? We need to come up with three things. Okay? So the three things, so we can introduce comma, comma, question mark, comma, question mark, comma, question mark. Okay. So what is the inverse to map of f? Map f, little f. When g is the inverse to f. Map f, little g. Okay, that sounds good. Why is it the case that that is inverse to the thing we said it was supposed to be inverse to? Well, what do we have to prove? Let's look at the context. Okay, so what we have to prove is that given any x in A, I think I'll just do this one on the board. Map f, map f, g of x equals x. Yes? Did I correctly transcribe the goal? Yeah. Okay. Other direction. G, f. Okay. Why is that true? Fusion, number one, that's the same as map f g compose f x. Okay, good. Now what? Yes. Map f lambda y dot y, because this thing is the identity function by alpha, right, which says that for all blah, 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 right? So we know that f and g are inverse. Therefore, g compose f is the identity. Therefore, it's the identity function. And then map ID, right? So from the composition, or right here goes the composition, right here goes the unit law, here goes the fact that g compose f equals ID. We've got a proof that map takes bijections to bijections. Okay? So the fact that a functor preserves bijections just follows from functoriality. There's nothing else to say there. Okay? Okay. So I'm not going to type this one in. In the companion code, you can see a proof using equational reasoning. So there's this notation in Agda for equational reasoning. And the proof is exactly these 3 steps written out with these 3 reasons. So you can look at that in the companion code as sort of a step-by-step equational deduction. And so now what I want to do is finish off by applying this technology to prove that convert is a bijection. So what we want to do is to write a function called convert-bijection, which is going to be a bijection between databases. Okay? Okay. And the bijection between databases, let's just, yeah. Okay. So the bijection between databases is going to be given by convert. So the first component of that is convert, because it's convert that I want to show is a bijection. Okay? So now in the second component, oh, you can't do a non-normalized, can you? Just do meta x Agda 2 show goals. Oops. Okay. So, and then scroll down to 4. It expanded it. Oh, well. Okay. What we want to do is show that convert is a bijection. Unfortunately, it expanded the definition of bijection, so it's a little bit hard to read. Okay? But why is convert a bijection? Because it's defined by map, and map takes bijections to bijections. So we can apply map is bijection to the functor that we use to define convert. So that's called there. And then we need one more argument, and let's call that question mark. Okay? And the question mark, I think Agda's getting a little bit confused about the types here. But the type of the question mark is to show that swap is a bijection. Okay? So let's define a bijection between nat cross nat and nat cross nat, which we will call swap. So swap is a bijection between nat cross nat and nat cross nat. And swap is going to be defined to be a quadruple. First, it's the swap function. What's the inverse to the swap function? The swap function. Okay, and then let's leave 2 goals. Why is the swap function and the swap function self-inverse? Well, show context, show goal. I mean, goal and, yeah, that one. Okay. It's because, well, in fact, it's the identity. So Agda has eta expansion for pairs. So x is definitionally equal to first of x and second of x. So we can just do lambda underscore goes to reflexivity. And lambda underscore goes to reflexivity. Okay? Okay. And now, if we fill in swap there, we use the fact that map takes bijections to bijections in order to conclude that convert, which was defined by applying map to a bijection, is in fact itself a bijection. Okay? So using the generic composition and identity laws for this library that we defined, we get a really nice clean proof that when we take a bijection like swap and apply it inside some little bit of a data structure, the big function that we get that manipulates the whole data structure is a bijection. Okay? Any questions about that? I know we left some holes and went a little fast, but after this I'll post lecture notes and you've already got the solution. So if you need to look at it, that's okay. Yeah?
Just a detail, the fact that method bijection there is colored yellow is because it's method bijection.
I'm not quite sure why it's yellow on your screen. It's not giving us a error for, it's not giving a unification. So the yellow means that unification is not solving everything that you said it would, and it's not doing that for us. So there must be some discrepancy between your text and ours. Okay?
It's also not really yellow, it's yellow inverse.
Yeah, right. Yes. Okay. Okay, good? All right, so now let's do one more thing. I'd like to do one example of programming in homotopy type theory. And you've all seen homotopy type theory in Bob's lectures, so we can probably go through it pretty quickly. I've got an example in mind. Let's take a database where we have some dates in European format and convert it to a database with some dates in American format, or with the dates in American format.